Hi, I'm Sara, a postdoctoral research from Aalto University, and I wanted to talk today about this work that I'm doing right now. It's still ongoing work, and it's based on this nested particle filter framework that basically aims at doing parameter estimation of parametric dynamical systems in a Bayesian manner. So this work is basically a joint work with Nicola Branchini and Victor Elvira from University of Edinburgh, and also with Joaquim Míguez from Madrid. That was my PhD supervisor. Um, okay, so I want to first give a brief introduction to the setting we are interested in, explaining parametric state space models and how it's what is usually done in this kind of settings, the state of the art, both for state tracking and also parameter estimation. And then I will focus more on the framework of nested particle filters. That is the one that we are building on. Okay, so first of all, we are interested in some specific type of dynamical systems that can be represented by Markov state space models. So we have a state xt that represents the state of the system at the current time step or at current time, and an observation yt that is a partial and noisy version of the state. So both of them are going to be noisy. So they both have some additive noise, V and R. And they are modeled with these two functions, f and g, where f is a function of the previous state of the system that is parameterized by theta. And the same happens with the observational function g, that depends on the current state and some parameters theta. In terms of probability density functions, then what we have with this state space model, it's a prior distribution for the parameters theta and the initial state x0. And then we have available also the transition PDF of the state and the conditional PDF of the observation, that is yt conditional on state and parameters. That is going to be our likelihood. Okay. So in the standard or classical filtering methods, such as particle filters or Kalman filters, what they aim at is at computing the posterior distribution of the state conditional on previous data, all the previous data, and some parameters, theta star. In this case, theta star is assumed to be known in the sense that it's the true theta of the model or the true parameters of the system. So this type of filtering methods they compute in a recursive way. So at every time step, they compute two main things. The first of it is the predictive distribution, that is like the PDF of the current state, xt, conditional on previous observations up to t minus 1. And for this, basically what we need is to have available the previous posterior distribution that we computed at the previous time step, and we need to have access to the transition PDF that it's actually described by the state space model. So we have everything we need available. And once we obtain a likelihood or a new observation, sorry, we can compute the likelihood, okay? That we can evaluate the likelihood and actually update the predictive distribution into the posterior one, okay? So this is nice, this is good. There are many ways to do it. If it's a linear model, we have an optimal solution. There is the Kalman filter. If not, we can apply some important sampling-based methods, such as particle filters. But in practice, the problem is that the true theta or theta star is not known. So actually, we need to do both tasks of learning theta and the state. And to be more specific, we are interested in learning the posterior joint distribution of the state and theta. conditional on the data we have available at up to time t. So within this context, there are several state-of-the-art methods that aim at doing Bayesian inference or estimation of both theta and the state. They are the particle Markov chain Monte Carlo, PMCMC, that it was introduced by Andrew Doucet and Holstein in 2010. Also the sequential Monte Carlo square, that is Chopin 2013. And the last one that I am going to explain a bit more is it was introduced by Dan Krisan and Joaquin Miguez in 2018. That is the nested particle filter. So all of them are interesting since they are Bayesian. So first of all, they can somewhat quantify uncertainty on the estimation error. Also, they are quite general. They are meant for not for just for linear models, but for nonlinear, any type of them somehow. And all of them did some convergence analysis or some theoretical analysis to provide some type of guarantees. Usually it's when n grows, the number of particles they converge to the true posterior. And the reason why I want to focus more on the nested PF is that the first two methods, PMCMC and SMC square, are batched techniques. That means that not at every time step, but at some point in the time sequence, you will have to reprocess all the data from scratch, from Y1 to YT. As for example, if you change some parameter sample, you are changing the model, so you would have to rerun everything from scratch. And in the nested particle filter, they managed to propose a method that is recursive. That means that there is no need to rerun anything from scratch, even if you change the parameter samples. And still, they are able to provide some convergence guarantees that I will mention later again. But this method is still converging to the true joint posterior, even though we avoid this thing to run from scratch the whole data sequence. Okay. So the idea now is that I will explain a bit the nested PF framework. I'll try to do my best to explain it because it's sometimes it gets a bit dense in notation, and probably there are a couple of typos there lost. And feel free to interrupt me at any time. Sometimes I just speak too fast and I forget to pause. Okay. So as I said before, the main purpose or the main aim is to compute or estimate the joint posterior of the state and the parameters conditional on all the data, all the sequence of observations. So we can rewrite this as this product, right? It's a change product. So we are trying to divide the problem into two parts and deal with them separately somehow. The first one, that is the conditional distribution of the state or the posterior of the state conditional on theta and y. It's basically the aim of the classical filtering methods. So we know how to deal with this, how to estimate this posterior, but the problematic posterior would be this one, that is the main problem, or that is the key difficulty. Okay. So how could we try to apply the same principles or the same steps that we use for classical filtering in order to estimate the posterior of theta? What I would try to do first is to at every time step t, we would have like a predictive distribution for theta conditional on past observations. And if we can compute this likelihood, the likelihood conditional just on theta, we could update the predictive distribution to obtain the posterior one, right? Now the problem is that we don't have access to this likelihood. It's not described by the model, and yeah, we need to, we could approximate it though, and we could rewrite it like this. That it could be this integral where we are marginalizing out the state. So the likelihood would be available, provided by the state space model, but we need to make use of this predictive distribution of the state conditional on theta. And that's why the nested part comes in. So we introduce the filtering for the state inside the other layer, basically. So using conditional on a given theta, we could compute like the predictive distribution of the state. That is what we need for the likelihood. And actually, we could compute also the posterior distribution of the state conditional on theta. Okay. So doing this, we use the inner filter for two reasons. One of them is to compute the predictive, so we can obtain this likelihood to update the layer of the parameters. But we are also computing the posterior of the state conditional on theta. So once we have these two, basically we have all the information we need to compute the joint posterior of both. Okay. This is in the ideal case, I'm writing everything just like we have just the PDFs available. This is an integral, everything is nice. But the problem is how to actually implement this or how to approximate this these PDFs as well. There are multiple ways to do it. And I'm going to try to introduce how they got to this MPF implementation, okay? For that, I'm starting with a simple example or a simple way of how I would do it to start with, like even before encountering any problem, there will be problems. So the initial way or the first idea I would have to try to implement this nested filtering thing, it would be like, okay, we have a prior for theta, so we start drawing some samples from it. So this is my samples from the predictive or the prior of theta. And for each of them at every time step, I would have to run another filter, a PF, SMC, as you want. So for each theta I would run a filter of the state conditional on theta I. Remember that we do this in order to be able to compute the likelihood conditional on theta, that in a SMC or PF, it's needed to compute the weights of each sample of theta, okay? So in a standard PF, I think that actually I coded a bootstrap particle filter. That is the simplest one, let's say. We would draw samples from the prior. If we are at a different time step, it would be from well, this is the predictive. You need the transition and everything as I wrote before, but let's assume we can just draw a new sample at time t, conditional on previous data. And with a new data point, we can compute the likelihood and then obtain some weights for these samples, okay? Once you have that, we could compute the normalized weights, okay? And do some resampling if needed. Otherwise, we would keep the weights and the state. And once we have that, we use these weights or this likelihood in order to compute the outer weights, the likelihood conditional on the theta I that we use to run this PF. We would compute the weights that actually in this case, they depend also on the previous ones. They are accumulating over time. And at the end, we could approximate the posterior distribution of theta as a sum of of basically it's a set of samples and weights, okay, where the W is basically the normalized weight. Okay, but here there are several problems. First, the first of all is that the parameter layer or the theta samples at some point will end up degenerating, because basically we are just sampling from the prior and we are never moving from there. There is no dynamics in theta. So what will happen, especially if you have a bad prior, is that most of these weights will go to zero, and you will remain with just one sample with weight 1 after a few steps. I think I have it here. Yeah. After several time steps, the filter degenerates. And one possible solution for this is that we could change the set of samples at every time step as you are updating the, we are updating the, we are computing this posterior distribution. We could resample or get new samples from this posterior at the beginning of each time step t and run again the filters inside. But then we would have the same problem that they were having in PMCMC and SMC squared, because you are changing theta, you are changing the model. So the filter that you have here, even if you are at time step 100, then you have to run this for t equal to 0 until t equal to 100. And this basically is computational complexity of t squared, and it's not interesting. So how did they avoid this within the MPF? They introduced this thing that they called jittering. Okay, that is basically they are drawing the new samples from a kernel, this kernel KN, where basically they are doing the following. They are they are moving a set of particles, that is epsilon n subset of particles that depends on the total number of samples n. It basically means that you are just getting a small subset of the samples and you are moving them with this kernel kappa. And the rest, you are keeping them as they are. You are not moving them, okay? And this kernel kappa can be actually a pretty simple thing. Like it has to be an arbitrary Markov kernel with the mean theta prime, that is basically the initial sample that you had. And it has to have some finite variance. Like I actually implemented it. It's just literally adding some Gaussian noise. It's just that it has to be some variance that has to be somewhat controlled, like it cannot be infinite variance. And as long as you move the sample theta in this way, you can, basically what we are doing is like, even if we change theta, we are not rerunning this from scratch. We are reusing the previous posterior from the previous theta I, even if it was different. So it's an approximation. It's like, okay, let's just keep reusing the previous posterior, even if it was conditional on a different model, and we just keep going on. So if we do this and we just do this approximation for this subset of particles instead of for all of them, they can prove convergence to the true posterior if n is like asymptotically. It's an asymptotic proof, but yeah, if n is sufficiently large, then the whole method keeps converging to the true posterior. That I find quite unbelievable, but it actually works. Yeah, so this is the way I understood it the easiest. You have another option though, that is like defining this kernel such that you are actually moving all the all the particles instead of a subset. But then you would have to be super careful with this variance that you are introducing. It should be as a very controlled variance, and that also depends on the square root of n. But yeah, if you want to be a bit more arbitrary with the variance, as long as it's finite and you choose a subset that is smaller than this, then this thing still converges. So I think it's pretty cool. Okay. So I wanted to show how the whole algorithm would look if you add the jittering step. Okay, I will go through it again, through the whole thing. So assuming we start at time 0 with sampling some particles theta from the prior, we could run this at each time step. So we would start like doing some jittering over theta. So we would get some different theta, bar theta, with respect to the previous ones. And then for each one of them, we would run as an SMC for the state, basically. We would obtain predictive samples, conditional on this new theta, compute the weights, and do some resampling of the states, okay? Remember that in this case, we are never rerunning anything here from scratch. If we had some samples at xt minus 1, we are using those, even if we change theta I. And then when we finish the inner part, the inner ledger or second ledger, I don't know how to call it anymore, then we can compute the likelihood for this sample of theta. Okay, so we would compute these unnormalized weights that are basically based on the likelihoods we computed here. And then we could do some resampling. So based on these weights, actually the normalized weights, not the unnormalized ones, we could resample the whole set. The whole set means that use a resample theta I, but also all the state samples that are associated with this model. Okay, they go all together in a pack. So you resample them, and then you will have like a new estimation for the posterior distribution of theta, conditional on the observations, right? And basically, the joint distribution of theta and x would be composed by the weights and the set of particles x and theta. And that's it, I would say. If you have any questions, stop me, please. Just to finish this part, just to understand a bit or summarize a bit what I just explained. This framework is quite interesting because I think it's the only one that it's online for this Bayesian inference and state tracking at the same time. That means that we never need to reprocess anything from before then time t. It can be applied to generic parametric state space models. We are always assuming that theta is a finite object. I haven't tried to do anything with GPs or a GPSSM. It would be interesting though. And actually, what is cool is that it's online, and at the same time it has convergence guarantees. That is not, I think it's not that obvious why this is working actually. And then it has a few limitations though. That is why I wanted to introduce the new part. And is that you have to think that this jittering step is basically what it's allowing for exploration in the parameter space, right? Otherwise you wouldn't move. And that means that basically we are doing exploration in the parameter space by adding random noise. In our case, it was just we were just adding some Gaussian noise. So that means it's not a very efficient way to actually explore the parameter space, and if the dimension of theta is big, then it would take ages to actually find a good area or a good region of the parameter space, maybe. Another point that I wanted to talk about is that also not only the randomness, but also the how you set the variance of the noise can be very, very important and very annoying actually, because it would affect how fast this thing would converge to the true posterior, right? We know that when n tends to infinity, at some point this thing will converge to the true posterior, but depending on how fast you are, how fast you are moving the theta samples and how big is your variance, you will explore faster or slower the parameter space. So it's gonna affect a lot how long you have to run this until it actually converges. So it requires some tuning, the jittering, basically. And it's not obvious how to set it because it will depend on the model and on the range on the size of the parameters, basically. So that's why I wanted to do something more gradient based to help to direct a bit more the particles towards areas that make more sense somehow to speed up a bit the convergence. Okay. Any questions so far? Maybe I'm going too fast.
No, I don't think so. I think it's a very good pace. Are there
Okay.
any questions? No.
Okay. So I keep saying my stuff. Um, So basically, the idea that we got is that, okay, we could try to do some type of gradient-based thing or some Langevin dynamics to move some of the particles towards the higher areas of probability in the posterior. And we thought like it's actually, if we can do it somewhat in a way that it's still recursive, that you don't need to rerun anything really from scratch, then you would be joining two things that are very interesting. That is like you are using gradient-based uh, methods to do a smarter search in theta, and at the same time you keep everything with complexity that is linear with time, but it's not so obvious how to do it. We are having problems to see how we can actually compute this gradient of the posterior with respect to theta in such a way that we can avoid doing this reprocessing from scratch, right? Because if we, let's say that we move theta with this unadjusted Langevin algorithm, okay? What we are doing is just the next sample of theta is going to be something that moves from the previous one based on the score function, okay? That is the gradient of the log posterior with respect to theta. In this case, there is some stochasticity. We are adding some additional additive noise, but the main problem is how to compute this score or this gradient. Okay. So this is a problem, or it can be complicated because this gradient basically is divided in these two parts. If we manage to have a prior that is not too complicated or not too complex, this shouldn't be a problem, the gradient of the prior, of the log prior. But this gradient of the log p of the whole sequence of observations, it's a problem, okay? First of all, because it's intractable, first of all, and then, as I said, it's not recursive. We would have to, every time we change theta, we would have to reprocess the whole y1 to t to get this score, and then we would just break the whole like nice feature of the MPF, right? That is the main thing that was nice, that it's recursive. It doesn't need to restart from scratch. So with respect to the intractability, we would use basically some type of approximate scores. Okay, there are two of them introduced in this Pojagi's Duzet paper in 2011, where they introduced two types. One that is complexity ON, and the other one is ON square. Of course, the ON square is very good in the sense of like it has control, like the variance doesn't grow with time, but apparently the ON solution, the main problem is that its variance, the variance of the estimator grows with time t in our case. So I think in practice it kind of works, but I would like to see actually a good comparison of these two. But what I want to say is that basically there are options on how to approximate this score. Okay, that is not tractable. And then the other problem, the not recursivity one, it's a bit more tricky, I would say. We are trying to see or to explore how to approximate this score a bit more like it was done in the recursive maximum likelihood literature. That is that they, instead of actually looking to the whole sequence of time, they just look to this partial score, just to the last time step somehow. And this, in this literature, I think it's also introduced in the same paper, how to do this. In this literature, basically what they are doing is that they compute this this partial score, computing the score at time t, but with a theta, evaluated in a theta that was changing over time. That is what happened in the MPF, that we are actually changing theta over time. So we are actually multiplying like likelihoods that are conditional on different thetas, okay? And they are computing the one for time t, from theta 1 to t, changing, and subtracting the one of the previous time step that is also computed with a change in theta. And then you obtain the partial one, okay? Yeah, so if we do this, that we are still working on it, still coding it, I'm still not sure how well this will work. We would be changing this. So in the MPF, in the original one, we were doing the jittering step, right? Where for a subset of particles, epsilon n, we were doing this, applying this kernel kappa, that in our case was just a random noise, okay? A Gaussian noise. If we do the Langevin, introduce Langevin here, we would be substituting this kernel that is just a Gaussian noise for this, let's say, an approximated, an adjusted Langevin kernel somehow. I don't know even how to call it. I just came up with this name yesterday. And we would be moving this subset of thetas over a few, iteratively, a few steps, using this an approximation of the score, right? It's not clear which approximation is gonna be yet because we are exploring options, but we would do an approximation of this score. And hopefully the whole MPF would converge faster to the posterior, especially when the dimension is big. It should be way more obvious, the improvement, I think. Okay, so yeah, I've been telling it all the time, but why bother basically on doing all these things? It's basically because we think that we will speed up convergence to the posterior for sure, especially when the dimension is big, as I just said. And still, I think we can obtain some still strong theoretical guarantees and try to see even if we could provide something that is non-asymptotic. That I'm not that sure on that, but we could try to have a look into that. There are some works on Langevin dynamics and non-asymptotic convergence. So we still have to have a look into that. And yeah, this is a bunch of references. Maybe I went a bit too fast, but then we have more time to chat. I point out here the original MPF paper that is Dan Krisen and Joaquim Miguez, SMC square, PMCMC. And then about the gradient, I think I added here this non-asymptotic convergence for the gradient, for the ULA. And then the approximations of the score are in this paper, if you want to check it out at some point. And that's it. I'm open for chatting about any ideas where to apply this. Actually, I'm right now working on something more related to Bayesian experimental design, trying to, make an use of these algorithms. I think they can help on that. And yeah, like if you have any questions, I'm very happy to talk about it.